Newton's laws, this is a big one. As always, if you enjoy this channel, give us a like and subscribe. So, I'm actually going to break this up into 3 different episodes. So, we're in episode 1.6 right now, and we're going to do Newton's 3 laws and talk about all of the different forces involved in those 3 laws. In episode 1.7, I'm going to get more specific and do inclined planes, forces at an angle, and combination problems that sort of involve maybe angles or multiple parts of Newton's laws. And then episode 1.8, we're going to do Newton's law of universal gravitation and springs. So just to kind of break it up so that we don't have everything all crammed into one episode. So let's get to the first law. The first law is also known as the law of inertia. Now, there's 2 parts to this law. The first part deals with objects that are not moving, objects at rest. Part 2 deals with objects that are moving at a constant velocity. So part 1 says, objects at rest tend to stay at rest unless acted upon by a net force. Well, before we can really talk about the rest part, we need to define what a net force is. So an F net, a net force, just means a total or a sum. So if the net force is equal to 0, then we say that that object is in equilibrium. Now, we got to make sure that we understand that just because the F net is 0 doesn't mean that there's no forces acting on it. But if the net force ends up being 0, the forces cancel each other out, or there are no forces, then the acceleration of the object is 0. Now, the first part of this law says that unless there's a net force, so we're saying if there's no force on an object at rest, then it's most likely, well, it will, according to Newton, stay at rest. And that's because its acceleration is 0. So let's look at a couple of examples of this. Let's say we have a block that is out in space. Well, if the object is out in space and nobody's pushing on it, then in that case, the net force is 0 because there are no forces acting on it at all. Now, if we say at that moment it's at rest, its velocity is 0, then because there's no net force, there's no acceleration. And if its velocity is 0 and it's not accelerating, then it stays at rest. But what other situations could we have like this? What if we had 2 forces acting on it? We could call this force 1 and force 2. If these forces are equal and opposite, they will cancel each other out. And in that case, again, we end up with a net force of 0. If it's at rest, and the net force is 0, the acceleration is 0, then it will stay at rest. So there's lots of other combinations we could have. We could have a force up and a force down that cancel each other out. We could even have forces at angles. So for example, we could have a force like this, and then we have 2 forces like we've seen in the vectors unit where we did the parallelogram method, and this force cancels out with this force. That was called the equilibrant. Again, the net force is 0, so if the object is at rest and its acceleration is at 0, then it will stay at rest. We could also have unequal forces that add up to cancel out another force. For example, let's say we have a large force and a small force, but the sum of those 2 forces cancel out over here. In that situation, then the net force, the sum of these 2, cancel with that, becomes 0. I just want to stress that the first part of this law only deals with objects at rest. If it's already at rest, the net force is 0, then the acceleration is 0. The second part, part 2 of this law, deals with what happens when the object is already moving and the net force is 0. The first law is also called the law of inertia. This is an important word, And what inertia is defined as is how much an object resists acceleration. So if we push on an object, that object is going to push back on us. It's going to resist accelerating. So that amount that it resists is its inertia. That's also directly proportional to its mass. So these are essentially synonyms. When we talk about inertia, this is usually used in a qualitative manner. It's a description. So we may say a comparison between something that has a certain amount of mass and something that has more mass. We would usually use the word inertia in that case. We would say it has more inertia. Whereas we use the word mass when we're talking about numerical values. So this would be more of a quantitative. So rather than say we have 2 kilograms of inertia, we would usually say 2 kilograms of mass. But if you use these, you can use them interchangeably, and if you make a mistake and swap one out, it really doesn't matter because they do ultimately mean the same thing. Well, let's look at an example. Let's say we have mass m, and then we have another mass that's twice as much. So we would say that if we gave this a number like 5 kilograms, then twice as much mass would be 10 kilograms. So we could say the mass is 5 kilograms, the mass is 10 kilograms. But we could also say mass m has inertia, and this mass has twice as much inertia. Now it resists acceleration. So this one resists acceleration twice as much as this. So therefore, if we apply the same force, this one's not going to resist acceleration as much, and it's going to have a greater acceleration. This one has more mass, more inertia, so it resists acceleration more. So it has a lower acceleration for the same force. Now, we're going to get into problems like blocks on inclined planes, but there's often trick questions in which they dress the problem up to look like this complicated question that you need to do all of these different calculations. They'll give you the angle, and they might give you a force, and they might tell you its initial velocity is 5 meters per second. But then the question says, what happens to the mass? Well, the mass is independent of everything else that's happening to it. So if it's 3 kilograms here, whether it slides down the slope, gets levitated up, or whatever, the mass is still 3 kilograms. And that's true no matter where we go in the universe. So if we have a little mass down here, and let's say it's 1 kilogram, that's 1 kilogram on Earth. If we put it on the moon, it's still 1 kilogram. If we put it on Jupiter, it's still 1 kilogram. In fact, if it's out in space, it's still 1 kilogram. In all 4 situations, it resists acceleration. It has mass. It has inertia. Now, that's not to say that the force acting on it is the same. The force acting on it would be the force due to gravity, which would be its weight. So the weight would be greatest on Jupiter, and then the Earth, then the moon, and the force of gravity in space, the weight would be 0. The second part of Newton's first law deals with objects that are in motion. So objects in motion tend to stay in motion unless acted upon by a net force. So again, we're going to say if the net force is 0, unless we have a net force, then an object that's moving is going to tend to stay moving. So let's look at this back in space like we did for the other object. Except this time, instead of the object being at rest, it's moving. And we're going to say it's moving at a constant velocity. So it has some velocity that's not changing. If that's the case, then the net force is 0. There's no forces acting on it at all. If there's no net force, then its acceleration is 0. Let's look at another situation. This could be a block being dragged along a table or something like that. If we have a force of pull to the right and an equal amount of friction pulling the other direction, those forces cancel out, so the net force is 0. If the net force is 0, then the acceleration is 0. And if it's moving at a constant velocity, it's going to continue to move at a constant velocity. This situation is quite tricky, and we'll get into this one in episode 1.7. But let's just take a look at it real quickly. This is an example of a block that's sitting on a flat surface and it's being dragged. So perhaps that could be a block where there's a person and they're walking and they're dragging this block along the floor like that. So the person's pulling with a force like this. The force of gravity is pulling down on the block. The table is pushing up on the block, and friction is acting back. Now, if this is moving at a constant velocity, then we know that the horizontal component, which we could call Fpx, would cancel out with the force of friction. And the vertical component, which we would say is Fpy plus Fn would cancel out with Fg. So the net force of all these forces would cancel each other out. If the net force is all canceled out, we have 0 for the net force. If the net force is 0, its acceleration is 0. And if it was already moving, it's going to continue to move at a constant velocity. So let's just sum this all up. Newton's first law, the part 1, says objects at rest tend to stay at rest unless there's a net force. So if the net force is 0, the acceleration is 0, the object stays at rest. Part 2 says if there's no net force and the object is already moving, its acceleration is 0, so it's going to continue to move at a constant velocity. Newton's first law handles situations in which the net force is 0. When the net force is 0, the object's at rest or it's moving at a constant velocity. But what if there is a net force? Well, the formula is F net equals ma. On the reference table, it's written as A equals F net over m. It's the same formula. The only reason that this is useful is if we wanted to find the slope, and they give you a formula like that, and you wanted to see what that looked like, the slope of this line would be the acceleration. The other reason this is useful is because the units aren't always given as meters per second squared. Acceleration is meters per second squared, but the unit can also be newtons per kilogram. A newton per kilogram is a meter per second squared. So, I keep reiterating this, but it's important. When there's no net force, when F net is 0, it's either not moving or it's moving at a constant velocity. When there is a net force, the object accelerates. You get acceleration. And what could that be? What forms could acceleration be? Well, that could be speeding up. That could be slowing down. But it could also be a change in direction. Because acceleration is a vector. So all three of these are forms of changing velocity. So when there's a net force, you get acceleration. That acceleration might be speeding up, it might be slowing down, or it could be a change in direction. So let's look at a particular situation where this happens. Let's say the only force acting on an object is a force of push of 6 newtons. So in that case, we would say F net equals ma. And then we would sum up all the forces. What are all the forces? Well, there's only one. There's 6 newtons. Actually, I'm going to write that as Fp, force of push. And then let's put our numbers in. So we could say the mass is 2 kilograms, the acceleration is unknown, and the force of push is 6 newtons. So in this case, the acceleration is 3 meters per second squared. Another important part of this is that the direction of the acceleration is always in the direction of the net force. So in this case, the net force is to the right so the acceleration is to the right. We have to add one more part that's tricky, that often doesn't get tested, but it could come up. And that is, if the object was moving to the right and accelerating to the right, it would speed up. But what if the net force was to the right and the velocity was to the left? In this case, the velocity would be negative. The acceleration would be in the direction of the net force. So this would be an object that would be slowing down. So just have to be careful of that. So I set this problem up so that you can see sort of a different version of the same thing. Let's say we have two forces, so we could say force of push 1 and force of push 2. Then we would say F net equals ma equals force push 1 to the right minus force push 2 to the left. So we would say 2 kilograms times A equals 10 newtons minus 4 newtons, which would give us 6, and our acceleration comes out to 3 meters per second squared. Remember, it's to the right, so that's positive. So the acceleration is in the direction of the net force. 10 is bigger than 4, the net force is 6 to the right. So both of these gave us the same magnitude and the same direction. So 10 minus 4 is the net force in the same way that pushing only with 6 is the net force. What about a ball that's thrown up into the air? Let's say this ball has a weight of 20 newtons. That means at any point while it's in the air, the force of gravity acting down on it is 20 newtons. So a common question that gets asked, that people get wrong all the time, is what's the net force of a ball when it gets to the top? We know that the velocity is 0. We know that the acceleration is 9.8 meters per second squared down. But what's the net force? There's only one force acting on it. If there's only one force acting on an object, that force is the net force. So what's the net force at the top? It's 20 newtons. In fact, it's not just 20 newtons at the top, it's 20 newtons everywhere along this trajectory. Newton's third law says for every force there is an equal and opposite force. It sounds simple, but we have to be very, very careful as to which forces are acting on which body. So, if you push against a wall, you put your hand, or even I push down on this notebook, then the notebook ends up pushing back up on me the same amount. And that sort of is logical and seems easy. But when we start dealing with objects that start to accelerate, it's not as obvious. How can a car start to accelerate or drive down the road? Well, if you imagine that this car was on a perfectly frictionless surface, very, very slippery ice, and you pressed on the accelerator, the car would not be able to go forward. What actually propels a car forward? Well, the tires start to rotate from the axle and the engine, and that tire pushes on the road. So the force of friction of the car pushing on the road, specifically the tires pushing on the road, pushes the road to the left. The equal and opposite force in Newton's third law is the force of friction of the road pushing on the car. So let's take another example. Let's say we have person 1 and person 2, and these two people have different masses. Person 1 is much more massive than person 2. They have more inertia, and they're in a tug of war. If the larger person starts to pull the other person towards them, it seems like the force would be larger for the person that is winning tug of war, but this is not the case. What actually happens is the force ends up being exactly the same. This person cannot pull on the smaller person any more than this person pulls back. So what happens is this person pulls on the rope, which pulls on person 1. So force of person 2 then pulls back on person 1. So this person's force this way is exerted on this person, and person 1 exerts a force on person 2 in this direction. And those forces are equal and opposite. So if somebody can't pull more than someone pulls back, how does someone win tug of war? Well, there's a couple of factors here. One, there's also friction acting. And if the friction on this person is smaller than the friction for this person, then the larger person will win. The other thing to take into consideration is the mass. So if the forces are the same, this person, if there's no other forces, let's say we get rid of friction, then this person has more mass, more inertia, more resistance to acceleration. So they will accelerate less than the smaller, less massive person. Let's look at another one that's very tricky. What about a car driving down the road that hits a bug? It seems like the forces would be much larger on the bug than it would be for the car. But remember, the car can't push on the bug any more than the bug pushes on the car. So the force that the bug pushes on the car, this way, is exactly the same as the car pushing on the bug. They are equal and they are opposite. Why is this bad for the bug? Well, this force is very large for a very tiny, small, not very massive bug. Whereas in this case, the mass of the car is very large. It has a lot of inertia. It resists acceleration, so this force isn't very much. So the car doesn't experience much acceleration. In fact, it's close to zero, whereas the bug experiences a large acceleration. We could look at that in the same way for a truck that crashes into a small car. The truck has more mass than the little car. The force acting on them ends up being the same, but the truck has a lower acceleration and the car has a higher acceleration. It's really the acceleration that ends up doing damage to your body. Let's look at a couple of other examples. The Earth has a force of gravitational pull on the moon. The moon pulls back the same amount. Those forces are equal and opposite. And that's also true if we deal with protons and electrons. A proton is attracted to an electron. The electron pulls it in this direction, and the electron pulls on the proton. Now, remember that they don't have the same mass. A proton is much more massive than an electron. So this will have less acceleration, this will have more acceleration. So they won't meet in the middle, they'll meet somewhere over here closer to the more massive object. And what about this situation? An apple that is dropped to the earth. The apple is pulled down by the earth. What is the equal and opposite force of gravity pulling the apple down? Well, there's an equal and opposite force of the apple pulling the earth up. Why don't we notice the acceleration of the earth up if the earth is technically falling up due to this net force? Because the earth is so massive. The mass of the apple is smaller, and that acceleration ends up being 9.8 meters per second squared. We learned in the kinematics unit that the acceleration of a falling object near the surface of the Earth, when we neglect air resistance, is the same for all objects. The acceleration due to gravity, whether the mass is small or large, is still 9.8 meters per second squared. Well, how can that be? Isn't there a very large force of gravity acting on this mass? And this one doesn't have a very large force of gravity, so shouldn't this fall at a lower acceleration? That's what it seems like should happen. However, remember that this has less mass, so it's easier to accelerate. So not much force, but not much mass. Lots of force, but lots of mass. So when we look at this ratio of force to mass, whether we're dealing with a large mass object or a small mass object, if there's no air resistance, when an object is falling in a gravitational field, the acceleration is the same. And on Earth, that happens to be 9.8 meters per second squared. There are different types of forces, and if we're going to generally define a force is nothing more than a push or a pull. I've been mentioning the unit Newton. All forces are measured in newtons, and because pushes and pulls are in a direction, all forces are vectors. One of the most important types of forces to know about is weight. Technically, this is force of gravity, but think about what the force of gravity is. That's the pull down on an object, so that is its weight. I like to use the formula written this way. Fuga Muga, the force of gravity, the weight, is equal to the mass times gravity. Now, remember that this is not the force of gravity, this is the acceleration due to gravity. So this is the force of gravity, this is the acceleration due to gravity. This is also the strength of the gravitational field. So, if we were to put the units in here, mass, kilograms, and because this is an acceleration, it's meters per second squared. A kilogram meter per second squared is the metric international system unit of a Newton broken down. So these are the fundamental units of a Newton. The way it's written on the reference table is G equals Fg over m. I prefer Fuga-Muga when I'm solving equations, but this is good to see it as a ratio because we know the slope of any line is change in y over change in x. So let's put this on the y-axis and put this on the x-axis, and if we did a graph of this, we would get a direct relationship. And the slope is Fg divided by m, so that would be g. So this would be the acceleration, which would be g. This would be the strength of the gravitational field. So on Earth, that value is 9.8 meters per second squared. We could also say newtons per kilogram, and you'll see that on tests. They'll often use Newton per kilogram instead of meters per second squared, but they're the same thing. So on different planets, you have different strengths of gravitational fields. Typically, smaller planets or planets that are less dense have a weaker gravitational field, and larger ones have greater gravitational fields, maybe like Jupiter or Saturn. So let's just do a couple of quick calculations here. What is the weight of a 2 kilogram object on Earth? Well, we would just do Fuga-Muga, and we would say 2 kilograms times the strength of the gravitational field on Earth, 9.8 meters per second squared, and that would give us a weight of 19.6 newtons. Now, in space, we kind of have an interesting situation because when we talk about space, we're talking about far, far away from other planets, somewhere where there's no gravitational pull from anything. So super, super far away. In that case, the mass is still 2 kilograms. Mass doesn't change depending on location, but there is no gravitational field. So what's the weight of an object in space? It's 0 newtons. It has no weight. On the moon, if we do Fuga-Muga, the gravitational field is 1.6 meters per second squared. So that would give us a weight of 3.2 newtons. Now I want to point something out here. When we went from the Earth to space, the weight went from 19.6 to 0. We went from space to the moon. The weight went up to 3.2 newtons. So in each case, the weight was dependent on the location. The weight was dependent on the strength of the gravitational field. But notice in each case, the mass stayed the same. The resistance to acceleration, the inertia, does not depend on location. This is a super common question. We have an astronaut that is on some other planet, some non-Earth planet, planet Q. And they have a mass of 60 kilograms, and on this planet they weigh 222 newtons. What's the strength of the gravitational field? Well, we can just do Fuga-Muga for this. So we would say they're 222 newtons, that's their weight, Fg is weight, equals 60 kilograms, that's their mass, and finding G, the strength of the gravitational field. If you do the math on this, you get G is equal to 3.7 meters per second squared. We could also say newtons per kilogram. It's the same thing. So the field is weaker. So if this astronaut went back to Earth, what would they weigh? Well, on Earth, what stays the same? Their mass. So we could come back here and say Fg equals mg and find out what this person who has a 60 kilogram mass weighs on Earth. And that comes out to 588 newtons. Again, the mass remains the same, but the force of gravity, the weight, is different. Force normal, the symbol is F with a little n, is the force due to a surface. So if you are standing on the ground, that would be the floor. If you're sitting in a chair, it would be the chair. If you're driving down a road, it would be the road. And it's important to know that the force normal always acts perpendicular to the surface. So let's take a very simple situation of a person standing on the floor. If we did what's called a free body diagram, where we looked at all the forces acting on them, we would have the force of gravity acting down. Now we know that they're at rest. So according to Newton's first law, if the net force is zero, the acceleration is zero, and if they're at rest, they're not moving. So they're not moving. So how big does this force normal have to be? It has to be exactly the same size. So we could say F net equals ma equals, we'll call up to be positive, so that would be positive Fn minus Fg. Now, what is the mass times the acceleration? The net force is zero, so the acceleration is zero, they're at rest, so they're not moving. So this goes to zero. So then we could say 0 equals Fn minus Fg, and we could bring this Fg to the other side. So we could say that Fg is equal to Fn. So we know now that Fn is equal to Fg, so let's just replace Fuga with Muga, and Fn is going to be equal to 80 kilograms times 9.8 meters per second squared. Fn, therefore, is going to be 784 newtons. This doesn't have to be that complicated, because all we have to do is say that these are equal to each other, and if they're equal to each other, whatever Fg is, that has to be equal to Fn. Now that's not always true. This is only going to be true when we have a person or an object that's on a flat surface with no other additional forces in the vertical plane. But if we take a block, or a person or any object, and we tilt the surface, the force normal gets smaller. And the steeper the angle, the smaller the force normal becomes. We're going to get into solving these types of problems in episode 1.7. It's also important to know that scales read force normal. A scale does not actually read your weight. It just turns out that when you're standing on a scale, you're not accelerating, therefore the scale reads whatever your weight happens to be. But let's say you're on a scale inside of an elevator. If the elevator is at rest, then the net force is zero. So Fg is equal to Fn. So the force normal reads your weight. The net force is zero, so the acceleration is 0. What could this elevator be doing? Well, it could be at rest, but according to the first law, it could also be at a constant velocity. So when at rest or at a constant velocity, whatever the scale reads is the weight of the person. But let's say that the scale is at rest and then starts to speed up. You can't change the person's weight. That force of gravity is due to the force of attraction due to the Earth in the gravitational field. But to be able to accelerate upwards, the bottom of the elevator has to push on you more than the force of gravity. So now we have a larger Fn. Fn minus Fg is our net force. That produces an upward net force, which means we have an upward acceleration. What would the scale read? The scale would read more. What if the elevator was going up and then started to slow down? Well, again, we can't change Fg, that's your weight, but as you move up and the elevator starts to slow down, it stops pushing up as much. So now we have Fn minus Fg, we have a larger Fg, we have a larger downward component, we have a larger negative component, so now the acceleration is down, or we could say negative, either way. Let's look at this situation. This is, we talked about this a little bit earlier. This is a block being dragged across a flat surface here. And this is fairly complicated. The force of pull that is dragging the block can be broken up into two different forces. We can call this Fpy and Fpx. Now, if there is no other frictional forces or anything else acting in the plane, in the x direction, the net force is going to be Fpx. If there is a small force of friction, then it would be Fpx minus Ff. And if the force of friction was equal to Fpx, then the net force would be 0, and the block would either be at rest or at a constant velocity. But let's just ignore the x direction for a minute and look at the y direction, because that's really the trickiest part. We know that the block is not levitating or falling through the floor, so we know that the net force of the block has to be 0. So we have an upward component of Fpy, but it has to cancel out Fg, so there's an additional force up. What does that force have to be? That has to be the force normal. So the force normal is not equal to the weight in this situation because there's a component of Fp that's helping to relieve the pressure of the floor. So the floor feels less force normal, because Fpy is helping to push in the upward direction. Friction is a force between surfaces or between a fluid. So an example would be a box that we slide across a table. It could be taking a dresser and sliding it across the floor, or it could be taking a sled and dragging it across some snow. It could also be a fluid. So for example, if we take a ball and drop it near the surface of the Earth, and we take into account air friction, the air rubs against the surface of the ball and creates friction. So there's different types of friction. There's kinetic and static friction. And the first one that we'll cover is kinetic friction. And if you think about kinetic and that word kinematics was one-dimensional motion. This deals with motion in which the surfaces are slipping or sliding past one another. So if I take my hand and I drag it across the piece of paper, that's going to be kinetic friction. Basically, if you can hear a noise like then you're dealing with kinetic friction. There's a concept of how slippery a surface is. And the slipperiness is called the coefficient of friction. This letter is the Greek letter mu. It's not a U. It's sort of a U tilted on its side. And that's coefficient of friction, and it has no unit because actually it is a ratio. So on the reference table, there are a whole bunch of coefficients of friction. So each one of these is a value of mu. We're going to get into static friction right after this. So for now, let's look at kinetic. So if we have rubber on concrete and the concrete is dry, that value is 0.68. Why is this important? This would be a car tire on concrete. Rubber on ice, very low coefficient of friction, very slippery. These values can never be greater than 1, and if it was 0, it would be frictionless. It would have no friction whatsoever. So we have lots of different surfaces that we can find the coefficient of kinetic friction for. So rather than just use mu, when we're using it for kinetic, then we use the little k to let us know we're not doing static. When we do static friction, we'll put an S in there. So for the same surfaces, mu k is always less than mu s, or equal to it when the coefficient of frictions are very, very small. So we can see 0.68 is smaller than 0.9, 0.67 is smaller than 0.85, and that's because kinetic friction for the same surfaces is always less than the static friction force, the maximum static friction force. I'll explain the maximum part when we do static friction. Another important part of this is that kinetic friction always acts opposite the direction of motion. So let's say we kick a ball through the air and we don't ignore air friction. We take air friction into account. Well, as the ball is traveling along here, we know that at this point, the ball is traveling tangent to the circle, tangent to the curve there in this direction. So the force of friction is this way. What about a block that's sliding across a table? Well, if the block is moving to the right, the friction is moving to the left. What if we dragged a block up a ramp? Well, if the velocity is this way, that's the motion, then the friction is this way. What if we had a block and we just let it slide down a hill? This could be like a sled on a hill. Then the velocity is this way, so the friction is this way. The friction is always opposite the direction of motion when we're dealing with kinetic friction. So let's do an actual problem. The formula for force of friction, which is on the reference table, is Ff equals mu, the coefficient of friction, Fn. Because we're dealing with kinetic, we put that k in there. So let's say we have a block that's sliding at a constant velocity. And let's say that's a wooden block on a wooden table. So the first thing we need to do is find mu k. And that's where we use the reference table. So it's a wooden block on a wooden table. It's kinetic friction, so we're going to use 0.3. And the question is to find the force normal. Now, without them giving us the mass, we can't do it the way that I showed you before. We have to do this using friction. So if we look at this force right here, we can break this up into force of pull or force of push. We'll do pull. Force of pull y and force of pull x. Then we can do a right triangle. Using this from the vectors episode, we have the adjacent side and the hypotenuse. So that's going to be cosine theta equals adjacent over hypotenuse, or cos 60 equals adjacent, which is going to be our FPX, over the hypotenuse, which is 100 newtons. Cosine of 60 is 0.5. 0.5 times 100 is 50. So we have FPX is equal to 50. Here comes the most important part. It's moving at a constant velocity. Now, if it's moving at a constant velocity, that means that the net force is 0. So that means the Fpx has to be equal to the force of friction. So knowing that those are equal, we can say that the force of friction equals mu Fn. Because it's kinetic, we can put in a K. And we know the force of friction is equal to the force of pull X, 50 newtons, is equal to 0.3 times the force normal. So we divide through by 0.3, and the force normal comes out to 166.7 newtons. And that force is going to be up. Finally, static friction. Static friction occurs when the surfaces interlock with each other and do not slip. So even though the bottom of a box or the surface of a table seem very smooth, in actuality, at the microscopic level, the surfaces are sort of jaggedy. So the surfaces between the bottom of a box and a table sort of sit like this, and when you try to move one, they end up hitting each other. And that's what the static friction is. Kinetic friction is when you push so much that then they start to slide over each other. You may have noticed this if you try to push a desk across the floor. It's a very heavy desk. When you first try to push it, the force is very, very high. And then all of a sudden it's almost like a snap. And then it starts to slide, and then the force is lower. It's easier to push it once it starts to slide. And that's because static friction for the same surface is actually larger than the force of kinetic friction. So when these surfaces are interlocked here and they don't slip, that's static friction. But the problem with this is that the formula for static friction only calculates that maximum value. So if we have a box and the surfaces are interlocked and we pull on it a little bit, the surfaces pull back. So if I pull on it with 10 newtons, it's going to pull back on 10 newtons, but the force maximum might be more than 10 newtons. So this graph sort of illustrates that. If I start to pull on this box, then I'll start to get more and more static friction. These interlocking forces will increase, and they'll increase and increase and increase and increase until it gets to its maximum value. And at the maximum value, that's what the formula calculates. But then it'll slip. And when it slips, it drops down and becomes the kinetic frictional force. This value right here is always FF equals mu K Fn. So this formula is safe to use whenever, but you can only use this formula when you're finding the maximum force, perhaps like the maximum force needed to start getting a block to move, and we'll solve one right now. So here's the question. How much force is required to start a 10 kilogram steel block moving if it is on a steel table? So the first thing that we have to recognize is that to get it going, we have to overcome that maximum static friction force. So we're going to have to do FF equals mu SFN. Now, it told us it's a steel block on a steel table. So we need to look at steel on steel, and we're doing this for static, so that's 0.74. So we have FF equals 0.74, there's no unit, times the force normal. Now, what's the force normal equal to? Well, for a block sitting on a flat table, the force normal is equal to the force of gravity, the weight. And what's weight equal to? It's equal to mg. So we can put in mass, 10 kilograms. We're on Earth, 9.8 meters per second squared. And the force of friction is equal to 75.5 newtons. So, how else can you get tricked by this question? What if they give you a block that's sitting on a table just like the one that we just did, but they don't give you any of that information. And all they say is that the block doesn't move and that the force pulling on it is 100 newtons. Then what's the force of friction? The answer is 100 newtons. The force of friction has to be equal to the pull because there's no acceleration. The force of friction back is equal. So what if we pulled with 200 newtons? Well, if we pulled with 200 newtons and it didn't slip, then the answer is 200 newtons.